Hey, in this video I'm going to introduce a few things that we are going to use in upcoming videos, and we'll start off with object slicing. Object slicing occurs when an object of a derived class is assigned to an object of a base class, because the variables defined in the derived class are sliced, or basically cut out or ignored to form the base class object. I have an example here, class base, which has an integer x, and class derived, which publicly derives from the base class that has an integer y. Then in main I instantiate derived. Then I instantiate base, I create an object called base, and I initialize that to the object derived. Now this is where object slicing is going to occur because int y is going to be sliced from the derived object. Okay, if you think about basic member-wise assignment, both base and derived have the variable x, but only the derived object has the variable y. So it's going to assign x of derived to x of base, but it's not going to assign y because y does not exist in base. Just example, in Visual Studio I have the class base, which has an integer member, this x member, and I have this derived class as well, which publicly derives from the base class, and that has an integer y. I assign those some values, x is 1, y is 2, just for debugging purposes. Then in main I instantiate derived, so I create an object called derived. Then I construct base here, which I initialize to this derived. You can see we get a squiggly here, and this is not an error, of course, it's more like a warning. You want to try and avoid slicing. You can have some issues with slicing, and there are ways of avoiding that, and we'll talk more about that as we go along. And this is where the object slicing is going to happen. Of course, the derived class, which publicly derives from base, inherits the x member, whether that is private or not. Alright, that x member is part of derived, but y is specific to derived. And so when we initialize base here to derived, it's only going to copy over x, so y is basically ignored or sliced in that construction. And the same thing is going to happen whether you do construction or assignment. I'll just place a breakpoint right here, and I'll run the local Windows debugger. And in the locals window, we have the base object and the derived object as well. Okay, so base has an x and derived has an x as well, but it also has a y component. Let's do this here in the base class. I'll make this here x. I'll put that in a public section. And then following the construction of base right here, I can do something like this. Derived.x is 55. And then I assign derived to base. And now if I run the local Windows debugger, once it reaches this line down here or the return statement, whichever one you have, expand these in the locals window again. Both has updated, so we assigned 55 to the x component, which is actually part of the base component for derived right here. Okay, so x is part of base. And with this assignment, again, we slice derived, so only the x component is assigned to the x of the base object. And of course, y will remain 2. For this next demonstration, I've modified the classes quite a bit. So in the base class, I have a constructor right here with a default argument that will initialize x. Both the base class and the derived class will have a virtual toString function. Okay, virtual void toString, and in the body I print out, so I do console output base class, and with a new line, and I do x, colon, and then I print out x. For this example, x is in the protected section, because I'm going to use that in the derived class. Then in derived, I have a constructor right here. This also acts as a default constructor because it has arguments for both parameters. Default argument of 1 for xp and a default argument of 2 for yp. Yp is going to initialize the y member, which in this case for the derived class is in the private section, and we are going to use the base class constructor to initialize the base class part of a derived object. Then I have this virtual toString function again, which prints out derived class, in this case x, and it prints out x. X again is protected in the base class, that is why we have access to it in the derived class. We have another new line right here, and then I do y, and I print out the value of y. Before we get to main, let's go and create a function. And this can be any function. Let's say I have setters for the base class or the derived class, and you want to actually modify the state of those objects within this global function. This is now a global function, right? It's not a member function. But in this case, we are not going to do something like that. We are just going to stick to a simple example just to illustrate object slicing again. I'm just going to do a function void display. And in the parameter, you can see this is a pass by value function. So we do base and base p for base parameter. Then I'm going to do base.toString here. Then in main I construct base, which is an instance of the base class, and derived, which is an instance of the derived class. Of course you can do base.toString or derived.toString. But for this demo I have this display function. Again, this can be some other function that does some operations on the parameter, and then following that you want to do maybe a toString call for debugging purposes, of course, to check the state of that object. But again, for this example I have a simple display function which is going to call the toString function on the parameter. Okay, so I'll call that global display function and I'll pass in base as an argument. And if we build and run this, we sort of get what we would expect. It prints out base class and it prints out x is 1. Remember that we have a default argument right here in the base class constructor. So let's do that same function display, but in this case we pass in derived. And because the toString member functions of base and derived are virtual, you would expect this to be the derived that prints out, and we should expect x and y to print out. But instead we get base class and we get x printed out. So in other words, the virtual, this toString function of the base class got printed out, and not the one from the derived class. And the reason why that is because if you pass by a value like this, okay, right here we have a base class, but we are passing in a derived class. That means we are going to get object slicing. So how can we avoid that? Well, we can do pointers or references instead. So just as a quick demo, I'll change this right here from pass by value to pass by reference. Okay, so this parameter is now a reference to a base class. And now if we do display and we pass in derived, build and run that, and we would now get derived class, x is 1, y is 2. And just to make sure, we pass in base to display, and that will work fine. It prints out base class, x is 1. So this right now, because we are passing by reference as opposed to passing by value, we are no longer doing object slicing, and as I mentioned, you want to try and avoid doing object slicing. Okay, we can pass by reference or by pointer to avoid object slicing. Back in Visual Studio, we are passing by reference right now. You could actually pass by reference to base constant. You could just add const right here, since we are not trying to modify the reference. But let's just go and change this here to a pointer. And then we'll have to change this here to a arrow operator as opposed to a dot operator. Then in main, I'll change these here to pointers. And I'll do something like this. I'll allocate a new object on the heap for a base, so a base object. And I'll assign that address to the base pointer. And the same thing for derived. I'm just adding some numbers here in the constructor. So for the base object on the heap, that has a value of 5. And then for the derived object right here, 33 for x. That value will be used to initialize the base part of the derived object, which will of course initialize the x member. And then we have 55, which will initialize the y member of the derived object. And then I simply do display base and display derived. Build and run, and the first printout we get is base class x is 5, and then derived class x is 33 and y is 55. You can see with the second call we sort of get what we would expect. So we do not get object slicing when we use references or pointers. And if you are still confused on why this is important, well, it's important because derived, right here, derived, this derives from, publicly derives from base. So it means that derived is a base, okay? And so because a derived class is a base class, we would expect that we can pass a derived object to a function that accepts a base class. That is what we can do now, and we get the functionality that we would expect. and that is thanks again to the virtual functions, okay, the virtual keyword, and also using pointers and references instead of passing by value. Otherwise, again, we'll get object slicing. Next, I want to show you what an upcast and a downcast is. Now, an upcast is when we cast from a derived class pointer to its base class pointer. You can see an example here. I have a pointer to derived named derived, and I create a new derived object, and I just pass it to integers for initialization. Then I do an upcast from derived to base. You are familiar with casting at this point. We put parentheses before the particular variable or object that we want to cast or convert, and we put what we want to convert it to between the parentheses. So in this case, we convert that derived pointer to a pointer of type base. So that is an upcast from a derived to a base. We can also do a downcast, and that is when we cast from a base class pointer to a derived class pointer. It's important to note that this is not always safe, and you want to make sure to use virtual functions. And we'll look at some examples in the next subsection. So the downcast example is at the bottom of the slide. We have a pointer to base called base, and I assign a new object on the heap, so new base, and I just pass it a value of 33 for initialization, so the constructor will accept that, and then I go and downcast from a base to a derived. So I have a pointer to derived, name derived, and I assign what to that? Well, I assign that pointer, okay, so it's going to copy the address, but before the assignment happens, we are going to do a casting or a conversion from the base pointer to a pointer to derived, okay, as you can see between parentheses. The recap on upcasting and downcasting. You upcast when you are casting from a derived to a base, or from a child to a parent. So basically you are casting up the inheritance chain or up the inheritance hierarchy, and with a downcast you are casting down the inheritance hierarchy or chain. Okay, so from a base to a derived, or from a parent to a child. For this example, the base class and the derived class are the same as for the previous subsection. So I have the constructors, the virtual toString functions. But now I want to demonstrate an upcast from a derived object to a base object here in the main function. So I have a pointer to derived, which I name derived as well. And here I create a new object on the heap, a new derived object. And I initialize that to some values, so I have 33 and 55 that I pass in as arguments. Next I have a pointer to a type of base called base. And this is where we do the upcast from the derived to the base, alright, to a pointer to base. And then we can do base, the arrow operator, and toString. And you can think for a second what's going to happen now. Are we going to use the toString function of the base class, or are we going to use the toString function of the derived class? Well, let's build and run that to see what happens. And we actually get the derived class toString. So we get derived class, x is 33, y is 55. We can also do an implicit upcast. Comment that line out, and then here I could have actually just copied and pasted this part right here, but in any case, so we are going to upcast implicitly from a derived to a base. Where you use the brackets as in the previous example, that is an explicit casting basically, or conversion, as I explained in previous lessons, but this is going to be an implicit upcast. If we build and run, we should get the same result. Okay, now let's look at a downcast. So we're converting the base pointer here to a pointer of type derived. Now let's do derived toString. And you can see we still get derived class, x is 33 and y is 55. If we have to look at what is on the heap. This base object is now on the heap, and what we're trying to do now is we're trying to downcast to a derived. In this case, what we get is a base class actually, and that prints out 33. You can see that is different from what we had previously, and that is because of what is on the heap. Previously we had a derived object on the heap, whereas now we have a base object on the heap. And that is why downcasting is not always safe, because the base object does not have the members that a derived object will have. But thanks to the virtual functions, the toString function of the base class is gonna get called. So it does work, but we do not have the members that we would expect from a derived object. That is in the case where we do a downcast from a pointer of a base object to a pointer of a derived object. Quick example again, when we do an upcast from a derived to a base, you can see in main I have the derived pointer. Okay, so that is a pointer to a type of derived. And we create a new dynamic variable on the heap. So we do new derived, and we pass in the arguments of 33 and 55, and that is going to initialize x to 33 and y to 55. Now x basically forms part of the base part of the derived object, and that's not really illustrated here on the heap with this object, simply because we know that we inherit that variable x anyway, so we have x and y, and those are initialized to those values. In the next statement we declare a pointer called base, and that is a pointer to type base. And we initialize that to what? Well, we are going to upcast from derived to base here. So between parentheses we have pointer to base and we have derived. So we're going to upcast from derived to base. The important thing to note here is the object that is on the heap. The object on the heap is a derived object. So it has the inherited x and it has the specialized y. Then in this next example we upcast implicitly from derived to base. We will declare a pointer called base that is a pointer to a type of base, and then we allocate a new dynamic variable on the heap, so new derived, and again we initialize those members x and y. Then in the next statement we downcast from base to derived. We've seen this example, but the important thing to note with this slide and with the previous slides is that we have an object of type derived on the heap with x and y members. X again is inherited, and then y is specific to derived. Now take a look at this example. This is different because in the first statement we again declare base, which is a pointer to type base, but then we go and allocate a base object on the heap. Okay, so we do new base and we pass in 33 for the construction, but the point here is that that is a base object that is now on the heap. Then when we go and downcast from base to derived in the next statement, this is often where the problem comes in and why it's not always safe to downcast from a base to a derived. Of course, in the previous examples we used a virtual function, and the object on the heap in this case is a base object. Let's say you do derived, the arrow operator and toString. It's actually going to use the base class's toString function. But what if that was not the case? So what would happen if you did not use virtual functions is you would actually call the toString function of the derived class. But again, on the heap we now have a base class object. So for your y component you will actually have garbage. Okay, and that is what I'm going to demonstrate next for you in Visual Studio. Right, I'm back in Visual Studio and I'll go and remove these virtual keywords from the toString functions of both base and derived. Then in main I have this example right here. So we declare this pointer derived, which is a pointer to derived, and look at what we allocate now on the heap. Okay, we're going to allocate a derived object on the heap. Then we are going to upcast this derived. It's going to change basically the type to a pointer of type base, and we assign that to the pointer called base, which is a pointer to a base. Then we simply do base, the arrow operator and toString again. If we build and run that, so this basically works fine. Base class, it prints out x. So it will not print out the derived version because the function is not virtual. Okay, so it's actually going to use the base class function. So let's change the example around a bit. This is going to be an implicit upcast from a derived to a base. Okay, and you assign that address to a pointer called base, which is a pointer to a base again. Next we have a derived pointer, which is a pointer to a derived. And now we're going to downcast this right here, which is a pointer to a base to a pointer to a derived. Then we do derived toString. And as you might have expected, we get the derived class function call now, so we get derived. X is 33, Y is 55. Again, I'll make some changes here. Notice again what we allocate on the heap. This is a base object, so it only has the X member. Then we do this statement again, the pointer derived, pointer to a derived, and we are going to downcast base from a pointer to a base to a pointer to a derived. And we do derived toString again. Now I can think for a second what's going to happen. Remember that we have a base object on the heap now and not a derived object. Let's build and run that. And as you might have expected, for y we get garbage. So it's going to call the toString function of the derived class, even though we do not have a derived object on the heap, and that's because we call it from a pointer to a derived. X is 33, which is correct, and we get that from the object on the heap, but y is going to be some garbage value. Alright, so that is the problem that you have with downcasting from a base to a derived. Once again, we can avoid these sort of problems by using virtual functions. So I'll change those toString functions to virtual void toString, and then in the main function the code remains the same. Let's build and run, and now the correct function is gonna get called, the toString function of the base class, because that is the object that we have on the heap. It simply prints out x. We did not get any garbage value for y, and that is the end of the program. Alright, so I hope this video was interesting to you and that you can see the value in using virtual functions and why you should avoid object slicing.